Welcome back to Engineering with Sophia. This is the deep dive, where we take complex engineering concepts, strip away the noise, and really hand you the foundational understanding you need to feel instantly well-informed.
And we get to treat the laws of nature like they're these beautifully structured puzzles. They're just waiting for the right solution method. It's always a good day when we get back to the fundamentals.
I'm Sophia, and joining me again is our expert, ready to guide us through our stack of sources today. We are continuing our exploration of heat transfer, but we're moving away from differential equations, which, let's be honest, can intimidate. Well, pretty much anyone.
They can, so we're moving into the realm of algebraic shortcuts.
Exactly.
That's right. Our mission in this deep dive is to take steady heat conduction problems, the ones involving composite materials and different boundaries, and solve them using what is probably the single most powerful tool in thermal engineering.
Which is the concept of thermal resistance.
Thermal resistance, exactly.
We're basically taking the principles of electrical circuit analysis, Ohm's law, something most people have heard of, and we're applying them directly to how heat flows.
Yeah.
If you understand how a simple electrical circuit works, you are honestly already halfway to mastering this entire part of heat transfer.
It's true. The key learnings for you today, the learner, are all about understanding how these thermal resistance networks are built. We'll look at simple and multi-layer geometries, how convection and radiation fit into the circuit.
And we're going to spend a lot of time on why the resistance of trapped air is so important, especially in things like building a house.
Oh, absolutely. And then finally, we'll dive deep into the microscopic and often overlooked challenge of what's called thermal contact resistance.
Okay, let's jump straight in. Let's build the foundation and define the conditions that let us use this beautiful shortcut.
Let's do it.
So we have to start with steady conduction. Let's establish this bedrock principle. What does steady conduction actually mean for the energy inside a material?
Steady means time invariant. It's that simple. It means that if you check the temperature at any point in the material right now, and then you check it again in 5 hours, it hasn't changed.
Okay.
And crucially, if we think about a solid medium, say a house wall on a freezing winter day, and the indoor and outdoor temperatures are constant,
Right.
the amount of energy stored inside the wall itself is not changing over time. So the rate of change of energy of the wall, dE wall over dt, is zero.
That's the key physical principle because it forces a really simple energy balance. If the wall isn't, gaining or losing energy over time, then the rate of heat transfer coming into the wall
Has to exactly equal the rate of heat transfer going out.
Exactly.
Precisely. We can write that as Q dot in equals Q dot out, and that whole thing is a constant. This constancy of heat flow is what makes the electrical analogy work so perfectly.
Okay. And for a simple case, like a big flat wall on a building, we can assume the heat is only flowing in one direction, right?
It's predominantly one-dimensional. It just moves in the x direction perpendicular to the surface.
So we can track the temperature as a function of distance across that wall, T of x. Now, this leads to a really fascinating result from Fourier's law, as long as there's no heat being generated inside the wall, like from a hidden heating element or something.
Yes, and this result is, it's probably the most elegant way to visualize steady, one-dimensional heat flow. The temperature distribution through that wall is not a curve.
It's a straight line.
It's a straight line. The temperature just varies linearly with distance x, and that linear profile is the visual proof that the rate of heat flow is constant at every single point in the material.
I want to pause here because this is often a conceptual hurdle for people. What if the wall is made of 3 different materials, like brick, then foam, then drywall? Is the temperature profile still one single straight line?
That's an excellent question. No, it's not one single straight line across the entire structure. It's what we call a piecewise linear profile.
Ah, okay.
So within each individual material, the line is straight. But the slope of that line changes, sometimes dramatically, at the interfaces between the materials.
And why does it change?
Because the slope is dictated by the material's thermal conductivity, its K value. A really steep slope means it's a poor conductor. It has high resistance. A shallow slope means it's a good conductor, low resistance. But within each single layer, it's linear.
That distinction is so important, and it's that constant heat flow rate that allows us this mathematical freedom. Lets us use algebra instead of calculus to solve for temperatures and heat transfer.
Which brings us to the great shortcut, thermal resistance.
Okay, let's unpack this using the electrical analogy. Everyone remembers Ohm's law from physics class. Electric current, I, equals the voltage difference, delta V, divided by the electrical resistance, Re.
The parallelism is it's striking. The driving force for electric current is the potential difference, the voltage.
Right.
In our thermal system, the driving force for heat flow is also a potential difference, which is the temperature difference, delta T hot minus T cold. That is the thermal equivalent of voltage.
And the flow itself, the electric current I, that's a perfect analog for our heat transfer rate, Q dot, which we measure in watts.
And naturally, the electrical resistance, Re, is analogous to our thermal resistance, R. So we can write the fundamental equation for steady heat flow as Q dot equals delta T divided by R total.
The elegance here is that it lets us look at something really complex, like a skyscraper wall, and just boil it down to a simple circuit diagram with a few resistors.
Now let's define the three main types of thermal resistance that we're going to see in these circuits, starting with the most fundamental one, the conduction resistance for a plane wall, R wall.
And that resistance comes directly from Fourier's law, and it's defined as R wall equals L divided by Ka. L is the thickness, K is thermal conductivity, and A is the area.
This simple ratio gives you immense engineering insight right away. To effectively resist heat flow, to be a good insulator, you have two choices. You either increase the thickness, L, or you decrease the thermal conductivity, K. And when you think about materials, high-performance insulation like styrofoam or fiberglass, the whole goal is to get the lowest possible K.
And why are those materials so effective? It's not really the material itself, is it?
Not really. They are largely composed of trapped air. Air has an incredibly low thermal conductivity, something like 0.026 watts per meter Kelvin. The solid structure of the fiberglass or the foam is really just there to trap that low air in tiny pockets.
So it prevents the air from moving and transferring heat by convection?
Exactly. The solid part is almost secondary. The low density and the high porosity are the key design features for good insulation.
Okay, so that covers conduction through a solid, but heat has to get to the solid and then from the solid. That happens through convection and radiation. How do those boundary conditions become resistances?
For that, we turn to Newton's law of cooling for convection. It says Q dot con V equals H times AS times the temperature difference. If we rearrange that to fit our circuit analogy, we define the convection resistance, R con V, as 1 divided by HAS.
Ah, I see the inverse relationship there. So the resistance is inversely proportional to the conduction coefficient, H, and the surface area.
And this formula tells us something really powerful about very efficient heat transfer processes, like phase change. If H is extremely large, approaching infinity, like during vigorous boiling or condensation,
Then the resistance, R con V, would approach 0.
it would. And in that scenario, with zero resistance, the surface temperature, Ts, must become basically identical to the fluid temperature around it, T infinity. It means that boundary offers almost no barrier to heat transfer at all.
Which is why engineers work so hard to increase H in things like power plant condensers.
Right? Then we have radiation resistance, Rad. Because convection and radiation often happen at the same time, we need to account for both.
Radiation is tricky, though, right? It involves the Stefan-Boltzmann law, which has temperature raised to the 4th power. That sounds too complicated for a simple linear circuit model.
It is more complicated, but we can linearize it for our network by defining a radiation heat transfer coefficient, HRAD. And once we have that, the resistance takes that familiar form. Rad equals 1 divided by HRAD times AS.
And the crucial nuance here, the thing that always trips people up, is that unlike HCOM, which we often assume is constant, HRAD is strongly dependent on the absolute temperature. You have to use Kelvin.
Yes. You can't just plug in a fixed number for HRAD without thinking about the temperature range of the surfaces that are radiating.
Okay, so let's put them together. A wall surface is exposed to air. Convection and radiation are happening at the same time. How do we draw that in our network?
They run in parallel to each other.
Why parallel?
Because the energy doesn't have to choose. It doesn't go either by convection or radiation. It does both simultaneously across the exact same temperature difference from the surface to the environment. Think of it like two parallel lanes on a highway.
Got it. Carrying traffic from the same start to the same endpoint.
And since they are parallel resistances, we could use the reciprocal rule to combine them. But for practical applications, especially when the surrounding temperature is close to the air temperature, we simplify.
We just use a combined heat transfer coefficient.
Exactly. H combined equals H con V plus HRAD.
And that's a huge convenience for engineers, right?
It is. It lets us collapse those two parallel paths into a single equivalent resistance. And that keeps the rest of our analysis purely in series, which is just mathematically so much easier.
Okay, now that we have the individual components, conduction, convection, radiation, We can start building real-world systems. Let's imagine a typical wall. Convection on the inside, the solid wall itself, and then convection on the outside. 3 elements.
In series. The steady-state energy balance is what dictates that series arrangement. The heat flow rate, Q dot, must be identical through every single element.
So Q dot con V1 into the wall equals Q dot con through the wall equals Q dot con V2 out of the wall.
And because the flow rate is constant, the resistances are in series, just like current flowing through several resistors in a row.
Which means the total resistance, R total, is just the simple arithmetic sum of the individual resistances. R con V1 plus R wall plus R con V2.
And that gives us our master equation for solving the whole problem. Q dot equals the total temperature difference divided by the total resistance.
Now here's where we can bridge the gap between the circuit diagram and that temperature profile we talked about earlier. How does the size of the temperature drop across a layer relate to its resistance?
This is maybe the most crucial takeaway for an engineer because it instantly tells you where your thermal bottleneck is. Since Q dot is constant throughout the entire series system, if we just rearrange our main equation, we get the temperature drop across any specific layer. Let's call it layer I, as delta Ti equals Q dot times Ri.
Ah, I see. So the temperature drop is directly proportional to the resistance.
Precisely. If you're looking at a system and you find that, say, 90% of the total temperature difference happens across just one layer.
Then you know that layer has 90% of the total resistance.
You do. That thick layer of insulation is doing all the work, and the rest of the wall is almost irrelevant to the overall heat transfer rate.
This lets an engineer spot the most effective part, or the failure point, instantly.
And we can easily extend this to multi-layer walls, a composite wall. Think of any modern building. You might have cladding, a vapor barrier, insulation, studs, sheathing, drywall.
You just keep stacking those conduction resistances in series. If the wall has 4 layers, it has 4 L over Ka terms, plus the 2 convection terms at the boundaries. Our total just gets bigger and bigger.
And this framework is also essential for calculating those tricky temperatures at the interfaces. Once we solve the whole system for Q dot, we can find any intermediate temperature, like between the drywall and the insulation.
And how would you do that, practically?
You just treat the path from the indoor air up to that interface as a new, smaller circuit. You know Q dot, and you know the resistance of that smaller path. Then you just solve the rearranged equation for the temperature. It's incredibly flexible.
Before we get to the big window example, let's connect this to a term people might see in, building codes or on product labels, the overall heat transfer coefficient, or U.
This is purely a convenience metric. Engineers often like to write the heat transfer equation as Q dot equals U times A times delta T.
If we compare that to our series resistance equation, Q dot equals delta T over R total. Well, the relationship becomes perfectly clear.
UA must be the inverse of the total thermal resistance. UA equals 1 over R total.
So if you look at it per unit area, U is just the inverse of the total thermal resistance for that area. This is the U factor you see on Windows.
Exactly. A low U factor means a very efficient, high-resistance system. And the reciprocal of the U factor is the R value, which is what you see stamped on insulation.
Ah, so a high R value means better resistance, better insulation.
You got it.
So if you're shopping for insulation, you want a high R value. If you're shopping for windows, you want a low U factor. It's the same physics, just flipped.
That's all it is.
Okay, this next section is just a masterclass in why this resistance method is so powerful. It perfectly explains the huge difference between a single pane and a double pane window. Our sources give us a really specific scenario we can dig into.
Okay, so we're looking at a standard window, 1.2 square meters. The inside air is a comfortable 20 degrees Celsius. Outside, it's a very cold minus 10 Celsius.
So a total temperature difference of 30 degrees.
30 degrees, right. And we're given the convection coefficients. H1 on the inside is 10 and H2 on the outside is 40. And notice the outside one is 4 times higher. That's usually because of wind, which enhances convection.
Let's start with case 1, the single pane window. It's an 8mm thick piece of glass.
So we have our simple 3-resistance series network. Indoor convection, the glass itself, and outdoor convection.
The boundary resistances are R inside equals 1 over H1 times A, which comes out to 0.08333 degrees Celsius per watt, and R outside is 1 over H2 times A, which is 0.02083.
Now for the glass. Our glass is L over Ka, so that's 0.0008 meters divided by its conductivity and area, which gives us 0.00855 degrees Celsius per watt.
And right here is the shocking engineering insight. Just look at those 3 numbers, 0.08333, 0.02083, and then the glass at 0.00855.
The resistance of the actual solid glass is almost an order of magnitude smaller than the resistance of the air on the inside. The glass itself is a massive thermal bridge. It does almost nothing to slow the heat down compared to that thin layer of air clinging to the surface.
The bottleneck isn't the glass, it's the air film.
It's the air film. So if we sum these up, the total resistance for the single pane is 0.1127. That gives us a heat loss rate, a Q dot, of 30 degrees divided by that resistance.
Which is 266 watts through one small window.
266 watts is a significant continuous heat loss. But the real problem isn't just the energy bill. It's the impact on human comfort. We have to calculate the inner surface temperature, T1.
Right, so T1 equals the inside air temperature minus the heat loss times the inside resistance. So 20 degrees minus 266 times 0.08333.
And you get the inner surface temperature is minus 2.2 degrees Celsius.
Below freezing. This is why sitting near an old single-pane window in winter feels so miserable. Any moisture in the room hits that surface and just freezes. You get frost. And from a comfort perspective, you are literally a radiator for that window. Your body is radiating its warmth toward a surface that's below freezing.
It's a huge source of discomfort. And that is the driving force that led to better windows.
Which brings us to case 2, the double-pane window.
The fix is so simple, and it's all based on the physics we've been talking about, using the insulating power of trapped air.
That's it. We now have 2 thinner 4-millimeter layers of glass, but they're separated by a crucial 10-millimeter stagnant airspace. The glass conductivity is the same, but the air conductivity, K-air, is a tiny 0.026.
So our network jumps from 3 components to 5, all in series. The 2 thin glass layers, the air gap in the middle, and the convection on both sides.
The game changer is that stagnant air layer. Now, this is a really important conceptual point. We calculate its resistance using the conduction formula, L over Pa, not the convection formula.
Wait, that's a good point. Why conduction? It's air. Why don't we treat it as convection resistance? Because the gap is specifically designed to be very thin and sealed. If the gap were too wide, natural convection currents would start circulating inside, and they would transport heat very effectively. But when you keep the gap narrow, 10 or 12 millimeters is typical, the air is considered stagnant.
Meaning it doesn't really move.
Right. We assume minimal bulk movement, so the heat transfer happens primarily through slow, inefficient conduction across the trapped air molecules.
That distinction is absolutely critical. We're leveraging the low K of air, not the high H of a moving fluid.
So we calculate our air. It's 0.1 meters divided by 0.026 times 1.2. And that resistance alone, our air, is 0.3205 degrees Celsius per watt.
Wow. 0.3205. I mean, compare that to the entire single-pane resistance, which was only 0.1127. That one layer of trapped air provides almost 3 times the resistance of the entire original window assembly.
The air layer is the dominant resistor, by far. So when we combine all 5 resistances, the new R total is 0.4332. The system now has nearly 4 times the resistance of the single pane.
The reduction in heat loss is enormous. The new Q dot is 30 degrees divided by that new bigger resistance, which is just 69.2 watts.
We cut the heat loss by about 75%. This is the practical payoff of doing this kind of analysis.
And the comfort factor.
Yeah.
Let's check the new inner surface temperature. It's 20 degrees minus the new lower heat loss times the same inside resistance. The new T1 is 14.2 degrees Celsius.
And going from minus 2.2 to plus 14.2. That is a massive shift. The surface is now warm enough that frost is impossible, and more importantly, the radiant heat loss from people in the room is dramatically reduced. This one example explains everything about why double-pane windows are now the standard.
It really does.
So we just saw how air, when it's trapped and still, is a champion insulator. But we need to flip the script entirely now. What happens when air is trapped exactly where it causes the most damage?
You mean between 2 things that are trying to get rid of heat?
Exactly. Between 2 high conductivity components that are desperately trying to shed heat.
We built our whole network theory on this idea of perfect contact between layers. We assume the temperature at the boundary of one layer is the same as the temperature at the start of the next one. No drop.
But microscopically, perfect contact is a myth. It just doesn't exist. No matter how finely you machine a surface, it's rough. It has peaks and valleys. When you press 2 solids together, only a tiny fraction of the total area, maybe less than 2%, actually touches.
And the rest of the area, the vast majority, is these microscopic voids, gaps that are filled with air. And we just established that air is a terrible conductor.
Exactly. These tiny unintended air gaps act as highly localized insulation. They create a substantial and very unwanted interface resistance, which we call thermal contact resistance, or RC,
And this resistance causes a measurable temperature drop right at the boundary.
a very detrimental temperature drop, often.
So how do engineers even quantify this? It seems like it would depend on how rough the surfaces are, how hard you press them together, all sorts of things.
It does. So the total heat transfer across that interface is a combination of conduction through the few solid spots and conduction across all those hair caps. We quantify it using a term called thermal contact conductance, HC.
Okay.
And our contact resistance, RC, is just the inverse of that conductance. RC equals 1 over HC. But because it depends on all those variables you mentioned, roughness, pressure, cleanliness, it's measured experimentally. The data is all over the place, but we have established ranges.
And our sources say that typical values for RC fall between about 0.000005 and other 0.00005 square meter Kelvin per watt.
Right, so let's compare that range to the resistance of different materials to see when this actually becomes a problem.
Let's start with an insulator, a 1 centimeter thick layer of insulation with a K of 0.4. Its thermal resistance is L over K, which is 0.25.
Okay, so the insulation's resistance is 0.25. The highest contact resistance is 0.00005.
The insulation resistance is thousands of times larger. So in this case, the contact resistance is completely negligible. You just ignore it.
You ignore it. Now let's switch to a good heat conductor. This is where contact resistance becomes an engineering nightmare. Take a 1 centimeter layer of pure copper. Its K value is 386.
So its resistance, our copper, is L over K, which is an incredibly small 0.00000026.
This is stunning. The resistance of the copper itself, 0.00000026, is now smaller than even the lowest end of the contact resistance range.
And it could be 20 times smaller than the high end of the range.
This is the critical takeaway. For good thermal conductors, RC can absolutely dominate the heat transfer path. If you are building a system designed to move heat efficiently, like a cooling system for a computer.
That interface resistance can completely negate the benefit of using copper in the first place.
It can. The bottleneck shifts from the conductor to the air trapped between the conductors.
So how do engineers fight this? How do you get rid of RC?
The goal is simple. Eliminate the air gaps. The most common solution is to apply a thermally conducting liquid, what we call thermal grease or thermal paste.
Right, the stuff you put on a CPU.
Exactly that stuff. It's a highly conductive fluid, usually silicone oil, that fills in all those microscopic valleys. It displaces the insulating air with a much more conductive medium, and that dramatically reduces the resistance.
Are there other ways?
Yeah, we also use physical methods. You can insert a very thin, very soft metallic foil-like tin or silver between the surfaces. Because the metal is so soft, it deforms under pressure and fills the gaps, vastly increasing the real solid-to-solid contact area.
Let's ground this with a concrete application. The sources have an example of a power transistor attached to a copper plate. Transistors get hot, and they need to dissipate that heat to survive.
So we analyze the heat flow. It's generated by the transistor. It has to flow through the interface, then through the copper plate, and then finally convect to the ambient air. It's a 3-resistance series.
R interface plus R plate plus R conv. Let's look at the magnitudes. The convection resistance to the air is usually the biggest number, right? In this case, it's calculated to be 4.0 degrees Celsius per watt.
The resistance of the copper plate itself, R plate, is, as we'd expect, minuscule, 0.00026.
And the interface resistance, R interface, assuming some typical surface quality, is calculated to be 0.030.
So the total resistance is 0.030 plus 0.00026 plus 4.0. So 4.0326.
What stands out here is the massive dominance of the convection resistance. That 4.0 is huge. The system's ability to get rid of heat is almost entirely limited by how well it can dump that heat into the surrounding air. That's the system bottleneck.
It is. But look internally. The interface resistance, 0.030, is still over 10 times greater than the resistance of the entire copper plate. And if the total heat flow is, say, 12.4 watts, that interface resistance alone causes a temperature jump of 0.37 degrees.
That seemingly small temperature jump located right where the heat is being generated can be the difference between that component operating reliably and burning out.
That's right. So even if our interface isn't the overall system bottleneck, it's absolutely critical for component-level design. You can't ignore it.
Okay, we've established the power of this series resistance idea for simple walls, but reality is often much more complex. Most structures have heat flowing in 2 or 3 dimensions.
Right. Think of a wall built with wooden studs and insulation filling the gaps between them. Heat doesn't just flow straight through. It will tend to flow laterally to get to the studs because wood has a higher conductivity than the insulation.
So trying to solve that precisely would involve complex numerical methods, which is exactly what we wanted to avoid today.
It is. However, engineers still rely heavily on the thermal resistance network for approximate solutions that are usually good enough. And to do that, we have to introduce the concept of parallel heat flow.
So let's consider that wall again. You have the high resistance insulation right next to the lower resistance wooden stud. They both span the same temperature difference from the inside surface to the outside surface.
But the heat divides. It flows through each path independently.
And that's the definition of a parallel circuit.
It is. The total heat flow is the sum of the heat flow through the stud and the heat flow through the insulation. And because the driving temperature difference is the same for both, the equivalent resistance is calculated using that reciprocal rule. 1 over R total equals 1 over R1 plus 1 over R2.
In a parallel system, heat always takes the path of least resistance. So if the wood stud has much lower resistance than the foam insulation,
The vast majority of the heat will bypass the insulation and flow right through the stud.
and this is what we call a thermal bridge.
Exactly. The stud, which you need for structural reasons, acts as a high conductivity shortcut for heat. And the resistance network lets us calculate exactly how much heat is being short-circuited that way.
So real-world structures are usually these complex networks with both series and parallel paths combined.
Yes, the composite wall is the classic case. You've got the inner convection resistance, then maybe a layer of drywall. Those are in series. Then you get to the main part of the wall, which has the parallel paths of the stud and the insulation. Then maybe another layer of sheathing in series, and finally the outer convection resistance.
And the approach is always to simplify the network. First, you calculate the equivalent resistance for the parallel parts, and then you treat that equivalent resistance as a single element that you add to the series path.
You got it. It's a step-by-step reduction of the network. And it yields a surprisingly accurate estimate of the overall thermal performance of the wall.
But we have to acknowledge the limitations. The heat flow isn't perfectly straight. It curves a little bit near the studs. So this 1D series parallel model is an approximation.
It is. And to handle that complexity without doing a full-blown simulation, engineers use two simplified assumptions that give us what we call bounding solutions. They won't give you the perfect answer, but they guarantee the true answer lies somewhere between their two results.
Okay, the first assumption is the isothermal plane assumption. What does that mean physically?
It means we assume that any plane that's perpendicular to the main direction of heat flow is perfectly isothermal. The temperature is constant across the entire area at that depth, whether you're in the stud or in the insulation.
That's a strong assumption. It basically means heat can move freely sideways to smooth out any hot or cold spots.
It does. And it simplifies the network, but it usually underestimates the actual resistance a little bit. It gives you a slightly higher predicted heat loss.
Okay, and the second assumption is the adiabatic line assumption.
Adiabatic means no heat transfer. So in this model, we assume all the surfaces that are parallel to the main heat flow direction are perfectly insulated. The heat flowing through the stud path is completely sealed off from the heat flowing through the insulation path.
So you treat them as two totally separate isolated paths that don't interact at all.
Right, and this method usually overestimates the actual resistance slightly, giving you a slightly lower predicted heat loss.
What's remarkable is how close these two bounding approximations often are. Our sources show that for one complex brick wall, the isothermal assumption gave a total resistance of 6.87, and the adiabatic assumption gave 6.97.
That hundredth of a degree difference is negligible for most engineering applications. Since the two extreme approximations are so close, we have very high confidence that the true 2D result is right there in that narrow band. It confirms that for long, flat structures like walls, the heat flow is mostly 1D, and the resistance network is a perfectly good tool.
This has been a really deep dive into how we can simplify the complex reality of thermal physics into these incredibly manageable algebraic circuit diagrams. It really revolutionizes how we approach steady heat conduction.
I think so. The core insight is that delta T equals Q dot times R. The temperature drop is directly proportional to the resistance, which just lets us instantly identify the thermal bottlenecks in any system.
And we spent a lot of time on windows, proving that the thermal resistance of a system is so often dictated not by the expensive solid materials, but by the boundary conditions and the strategic use of really low mochi materials, like trapped stagnant air. That gave us a 75% reduction in heat loss.
Conversely, in the microscopic world, we learned the critical counterpoint. where you need heat dissipation, like in electronics, eliminating those same air gaps with thermal grace is absolutely crucial to prevent contact resistance from limiting the performance of your components.
And finally, we saw how this resistance network is robust enough to handle complex, real-world structures with both series and parallel paths, bridging the gap between simple 1D theory and multidimensional reality.
We focused entirely on plane walls today, where the heat transfer area A is constant.
Right.
But what happens when the area changes as heat flows outward, for example, in a cylindrical pipe or a sphere?
That would change things. The geometry fundamentally alters the relationship between conduction resistance and convection resistance. As you add insulation to a pipe, you increase the conduction resistance.
But you also increase the outer surface area, which decreases the convection resistance.
Ah, so they're competing.
They're competing. And this competition leads to this highly counterintuitive concept of a critical radius for insulation. If the insulation layer on a small pipe is very thin, adding a little bit more insulation can actually increase the overall heat transfer rate.
Wait, so more insulation makes it lose heat faster?
For a short while, yes.
Impressive.
The benefit of the larger cooling area outweighs the resistance added by the material. It's a surprising result that defies basic intuition, and it shows that more insulation isn't always better. It's a fascinating concept for you, the learner, to mull over or explore on your own.
An excellent thought to end on. Thank you again for guiding us through the thermal resistance network.
My pleasure.
And thank you, the learner, for joining us for this deep dive into engineering with Sophia. Don't forget to subscribe this channel.